The next speaker, please welcome Josselin from Trail of Bits, who's going to be speaking about fuzzing, building secure contracts, how to fuzz like a pro. Welcome, Josselin.
Thank you. Okay, hey everyone. So this is going to be a workshop. We are going to have a couple of exercises we are going to go through. If you already want to take all the material, you can take the QR code or go through this website. You will see 5 exercises. I'm not expecting us to go through all of them. If we can go through maybe 3 of the exercises, it's already good given the time we have. But say if you want to, if you like challenge or if you're really fast, go for it. We have 2 spare tickets for the security summit. So if you go through the 5 exercises and you don't have a ticket to the summit, just let us know. Okay, today we are going to talk about property-based testing that was introduced in the previous talks, and we are going to have an hands-on approach on how to develop invariant and how to use fuzzing to develop more secure contracts. My name is Josselin Feist. With me, Natalie Chin and Justin Jacob from Trail of Bits. If you have any question about our company or about what we are doing, don't hesitate to let us know. Natalie already introduced us this morning, so I will skip this part. So today we are going to focus on kind of trying to understand how to find bugs in a contract, how to find vulnerabilities, what are the different types of technique we can use, and we're going to focus on a specific technique, which is property-based testing, as you guessed. Let's say you have this piece of code. You have 2 functions, a function to buy token and a function that computes some price, and you want to find bugs in this example. Don't try to look too much. There is a bug there, but we will see it later. How can you find vulnerabilities? On a high level, you really have 4 techniques that you can use. The first one is unit test, manual analysis, fully automated tool, and semi-automated tool. Unit test, I'm hoping that you are all aware of what they are. Basically, you create a concrete example, and you are trying to test it with different platforms, hard hat, Foundry, whatever works for you. Here, it's a good technique. It works well because it's well understood by a developer. But from a security standpoint, it's not going to protect you against vulnerability. We actually have data that highlights there is no correlation between having good unit test coverage or unit test development and the likelihood of having critical vulnerability in the code base. And the reason for that is that most of the time when you are going to develop unit tests, you are going to use them to trigger a happy path for things that should behave the way like you are intended to do, while vulnerability usually relies on kind of edge case. That's why you should still do unit tests, but they are not going to be enough. The second technique, just an example of unit test. The second technique is manual review. For this, usually it requires specific set of skills, specific mindset, and specific expertise. Usually for manual review, you are going to ask a security auditing team, such as Trail of Bits or any of our competitors, to look at your code and try to find vulnerabilities. This has some benefit. You will be able to catch any type of vulnerability. You will have a large coverage, but it has also some limitation. The first one, it's kind of done on a snapshot of your code base. It's time-consuming. It's resource intensive. The next technique you can use fully automated tool. Usually, this type of techniques rely on static analysis or analysis like static analysis. They are going to look for patterns, for common vulnerabilities that are well known in the space, and they are going to try to find vulnerability like that. You might know Slither, which is a static analyzer for Solidity. If you don't know, we actually have a GitHub action, which is called Slither action, where you can just add this to your CI. Every time you do a pull request, it's going to look for common vulnerability, and it will help you to triage the result. This is really powerful, and it's open source, and it's free. The last kind of type of technique, we call them semi-automated analysis, because then you need a human in the loop. You need someone to help the tool to know what they are looking for. And one of the main known technique for that, but we kind of discussed in the previous talk, is called property-based testing, and we are going to see what it is and how to do it with a kid now.
So as I mentioned as a precursor in the previous talk, when we refer to fuzzing, we're essentially stressing the program with random inputs, which means at a high level, it would be like a monkey on a keyboard or a cat on a keyboard, and essentially throwing random inputs into your smart contracts and seeing how your system behaves. Fuzzing in general is fairly well used in traditional software security, and you can see that through the use of, like, for example, AFL and GoFuzz. Generally, these platforms are testing for crashes. So they're looking for, are there opportunities in which malformed input can cause a program to crash and therefore cause unexpected behavior. That's not exactly what we're going to be testing with smart contracts because there is no concept of crashing. Instead, we're looking at property-based testing. So this is when you take some of the assumptions that you've made on your code base and you apply it through property-based testing by defining invariants. The fuzzer is basically going to generate random inputs, call your smart contracts, and check whether the output and the states are actually correct and whether there are deviations from what is expected. In general, fuzzing can also be considered as unit testing on steroids because you're not only limited by the input that you've specified, but you have the fuzzer comes with additional features to essentially generate different input. So in terms of what is an invariant and how are we able to actually use fuzzing to integrate, an invariant is basically something that always has to be true. It's something that, regardless of what a user does with your code base and how your code base works, this property is supposed to hold true within your code base for any state change. So the easiest example would be for the ERC20 token, that a user's balance should never exceed total supply. If this property is violated, then it means there's probably something as an error within like the mint function or maybe something within arithmetic. This property tells us that if there is a violation, that there is an underlying bug in our code base. So this is where Echidna is used. We use it fairly heavily in audits, and it's used very much in mature code bases. It's basically used to generate those random inputs so that we can call smart contracts and call those functions and see whether properties are intended to hold. So from essentially the invariants that we create, we're writing them into Solidity, into something that Echidna can understand and therefore run randomized inputs on to check whether there are potential invariant or property violations. So this is one example of smart contract code. And this is just the typical, this is just a standard token. It's got total supply, it's got balances, and it's got a transfer function. So if we specify that the property invariant is essentially, we are able to define it as an Echidna function, the Echidna test is going to generate random inputs to see whether a property violation is possible. So in terms of what the property actually is, we should be determining what code to put within the Echidna invariant to determine whether total supply and the balances assumptions actually hold. If Echidna is able to break this, then it means Echidna has essentially found a set of inputs that breaks those invariants. So pass it to Josselin for exercises.
Thank you. Okay. As I mentioned, it's a hands-on session. So we are going to see a couple of exercises, and we are going to help you to write invariant in Solidity and to test them with Echidna. Before we go around for like the setup, do you have any question regarding property-based testing, regarding fuzzing in general? Okay, so you can go on this website.
Hi.
Oh.
I have one small question. Do you know what's the difference between the property-based testing and the mutation testing?
Okay. Usually mutation testing, it refers to a technique where you are going to change the unit test. So you have like, a set of unit tests, and you are going to introduce change in your test or in your function to see if the unit test pass or doesn't pass. Kind of like the idea of mutation testing usually is going to rely on trying to evaluate how good your unit tests are. Here it's different, because here we are going to define invariant, and we are going to see if the invariant holds or doesn't hold. So mutation testing is usually more used to test the quality of your unit test. Here it's to test the invariant of the system.
Okay, thanks.
We have a tool which is called Necessist that does mutation testing, if you're curious. Okay. What time is it? So let's take 15 minutes to go through this first exercise. So if you go here, you can just follow the links. Okay, until 3:10. And we are going to go, over if you have any questions. We're going to go over if you have any question with the setup or if anything is not working. One caveat, we don't support yet SolC 0820 because of push 0. It's going to be supported in the next release. So you need to use SolC version B for 0.8.20. And you can use SolC select to easily switch between them. Let's give it 3 additional minutes and we'll go through the answer. Okay, so for the first exercise, this was a target. I'm assuming you can see, just by looking at the code that there is an obvious bug here. We are using uncheck on the arithmetic operation, so there is no overflow protection. As a result, you can easily do like an underflow when you transfer the funds. But how can you, without even looking at the code, how can you try to find this type of bugs? And here, the property that we want to try to see is this invariant that no one should have more than the total supply. If you deploy the contract and you say, like the initial balance is 10,000 and there is no min function, the total supply is 10,000. And now the invariant, the property is exactly that. The user should not have more than 10,000. As you can see here, something which is really straightforward is that you can define the invariant in solidity. Everything is in solidity. It's just a function with that return a boolean, like a condition, and this condition is our invariant. If you run a kernel on that, it's going to say, yes, I can break this invariant. Here is a sequence of transactions to trigger and to reach like this condition. And it's just a call to transfer with 10,000 and some number. And yeah, obviously it's because of the underflow here. Is there any question regarding the first exercise? How many of you managed to have Echina running? Okay. How many of you managed to finish the first exercise? Okay. So let's go to the second one. Here, we are going to try to have a system where you can pause the system, you drop the ownership, and we're going to use Echina to see if we can unpause the system. So let's take 15 minutes again, so 25.
then it will be also on YouTube.
So can you tell us a bit more about how Echidna works underneath? Like, does it just realize what the functions are and calls them in a random order with random inputs? For example, in this case with the pause unpause, I guess you just write this invariant saying, make sure the contract is not unpaused, and then it would just try out these pause unpause functions by itself.
So it's going to try all the functions of the contract. There are some heuristic. For example, we do constant extraction. So we are going to use Flitter to look at the code, find some interesting variable, and feed that to Echidna so that it's not fully random, it's random with some heuristic. Under the hood, it does coverage, so it's going to look at what are the different areas of the code that are reached by the transaction, and it's going to use this information to determine which mutation to apply. So it's not fully random, it's random with some heuristics.
So, for example, for the previous situation with the transfer, we only care about the balances and not the pause unpause mechanism. There is a way to guide the Echidna to say,
Yes.
This is the only thing you should use, try to break it with that.
Yes, there is a configuration file, so you can say, okay, just call 5 function, or just call this function. Like if you have a really large code base and you want to kind of narrow the search, you can do that with a configuration file.
All right, thank you.
Any additional question? Okay. Just to get a quick overview, how many of you managed to finish the second exercise? Oh, way more than the first one. Congratulations. Okay. So here we have a contract with multiple functions. We have a feature where the owner can pause and unpause the system. There is an only owner modifier, and so on. So the question here is, can we deploy the system in a way that the contract is paused? You drop the ownership, you put it to the address 0, so there is no more owner, the system is paused. Can you unpause it? And here, again, the property, the invariant, is going to be described in Solidity. It's simply this function. So it's a function that returns a Boolean, and the Boolean is a condition, is pause is equal to true. Yeah?
Yeah, so I thought we had to write a test that narrows it to you can't call resume, essentially, because in the test you're calling paused at the start, and if you're saying is pause is true, is always true, then it's not going to be true initially until paused is called and then ownership is renounced.
So, okay, if I understand correctly, and correct me if I'm wrong, you mean that to check if resume can be called was?
Well, I just thought that was what the exercise was.
Oh, okay, okay.
Because the test is not the contract, that's like a user. And you're saying the expected behavior is the user can deploy the contract, call pause, and then renounce ownership.
Yeah.
And you're testing that it can't be unpaused. But that test is saying that it's always paused from the start, but if that makes sense.
So, okay, like here the scenario is that you deploy the contract, you call pause, so you pause the system.
Yeah, because I'm seeing this as like separate from, like this test contract, I'm seeing it as separate from the token.
Okay, there is an inheritance here. So test token inherits from token. So you inherit all the functionality.
Yeah, I get that. I guess I'm thinking more for like Foundry tests, you have like a setup, and I was thinking the constructor is like the setup, but you're actually saying like that's the constructor of the token.
Yes.
And I see.
Yeah, okay, Foundry typically would have a setup function where you do like the initialization. We do support this kind of, let's call it an API. I have a couple of slides later on. So you can also use setup function and do it that way. Does that make sense?
Yeah, that makes sense.
Okay. Okay, where I was. Yes, so here the invariant is just the solidity function, is always pause. If you run Echidna on it, it will call two different functions and it will break the invariant. Here, just to remember, we did not look at like the different function. Maybe we don't even know there is like a resume function. We just say, I want to have this invariant. And what's going to happen is that Echidna is going to deploy this contract, is going to call all the different functions available in the contract, transfer, pause, unpause, whatever. It's going to try all of them. And in between every call, it's going to call the Echidna function, so the invariant. It's going to see if it's holding. And here what it does is that it does two calls, one call to honor, one call to resume, and after that, when it calls the invariant is broken. Why the invariant is broken? So this is kind of like a old style of vulnerability where like in old version of Solidity, you were defining the constructor with the name of the contract, and here there's a typo. The contract is called ownership, and the function is called honor. So honor is a function available for everyone. Anyone can become the owner, and then everyone can unpause the system. This type of vulnerability don't happen anymore, but it's just to give you like a kind of should not happen anymore. But just to give you like an insight of the type of invariant that require multiple transactions to be broken. Do you have any question regarding the second exercise? Yeah.
So regarding the functions you call, is it like brute force, or do you have any strategy on doing this?
So, as I mentioned previously, it's random, but with some heuristic, and one of the heuristic is using the coverage. So it's going to look at, like you make a new transaction with a different function. Are you covering new code? Yes, no. And based on that, there's kind of a feedback loop to know, where to kind of prioritize. But part of it is still random. I think there is like a...
Can you please go back to the previous slide?
Yeah.
I mean, it's a related question to the previous one. So in this case, owner doesn't take a parameter. But let's say that owner would take an address, and the owner is set to the address. In that case, would Echidna still be able to pass message.sender to the owner and still be able to find the bug?
Yes. Typically, as I mentioned, it's going to try randomly value for the parameter, but in addition to that, there are some heuristic. And one of the heuristic for address, for the type address, that is going to use all the address that are known within the execution. So your owner, any contract that you deploy, or things like that.
And what about interactions where a specific function needs to be called a few times and another function, a little complex interaction? So, I mean, does Echidna try those also, or?
Yes, it's like here. Here there is two transactions, but you can go like further, 5, 6, 7. Something that can happen also is that you call 20 transactions, you break the invariant, then Echidna has a strategy where it's going to try to reduce the call so that it's a bit easier to debug. So you might break it the first time by calling 20 functions, but then Echidna is going to try to say, oh, okay, maybe I just need to call 10 of them, and there's this process.
Okay, thank you.
Okay. Now the question that it's sometimes difficult, to have a good insight and to go behind is how to define good invariants. Like the example we just saw, the invariant was pretty straightforward, and they are simple. But when you're in front of a code base, the invariant might be more complex. So how can you kind of define them? How can you understand them? And I think the best process is to have an iterative approach. Start really small. The first invariant that you are going to describe for your contract should not break. Like the first invariant should be something really straightforward that should not break. It should be something just to kind of get used to the code base and get used to like the system. You should first define the invariant in English. Don't try directly to write them in Solidity. Open a Markdown, open a text editor, whatever works for you, and start to think about them in plain English, like what the system is supposed to do. Then write them in Solidity and iterate. You run Echidna, does it break? Does it not break? If it breaks, either you found a bug, or maybe your invariant is wrong. Maybe you made assumption about the code base, and the assumption that you had was not correct. So that's why you need this iterative approach, and that's why trying small is usually better because you remove complexity. As I mentioned, start early on, even before. It's kind of like a paradigm shift. Even before starting to code, like if you're a developer, before even starting to code your contract, you can think about what the system is supposed to do, and this will help you, down the line. So it's really like a process of thinking about what the system is supposed to do. Just to give you some example, if you have an arithmetic library, if you have like a fixed point arithmetic or something like that, then you can think about what are the arithmetic properties that you should have. Commutative, identity, inverse, and so on. So you have like a couple of math-related invariants that should hold for most of the properties. Then you have something that can be more complex. There is a supply, which we already saw. Then you can start thinking about some function, for example, transfer, what the transfer is supposed to do. The transfer is supposed to decrease your amount, right? And it's supposed to increase the amount of the receiver. If you go and you define an invariant that does that, you will realize that this is actually false, because one of the edge cases is that if you do a self-transfer, you don't decrease your balance is going to stay constant. This is just an example of invariant that might seem straightforward, but actually there are a lot of edge cases and things to consider when you are building these type of things. Something to consider also is situation where the system should revert. So, or return false. So it's also important to, create invariant on things that should not happen in that way. So if you have a transfer and you don't have enough funds, either you should revert or return false depending on your implementation. There are kind of two categories of invariant. You are going to have function level invariant. So those are going to be invariant related to the execution of a specific function. Most of the time, not all, but most of the time, they can be stateless invariant, so you don't manipulate the state. And those are usually the simplest to test, because you can just look at the specific function, and you can just focus on that. Then you have system-level invariant, so invariants that must be true for any function within the contract. The balance of the user not being greater than the total supply is one of these examples. So it's not just with respect to a specific function, but it's respect to the system as a whole. Now, how to do that in practice? For function level invariants, a simple technique is just you inherit the target, you inherit the function, you create a function that you want to test, and you can use, for example, assertion to check. So you can say, here you test the commutative, I and B, and you test that it's equal to B and A. System-level invariant might have more complexity in the sense that you might need a complex initialization. Maybe you're going to try something that requires 5 different contracts, and then you need to deploy the 5 different contracts. For that, either you can do everything in Solidity, or you can also leverage your unit test to do that. We have an additional tool, which is called Ethino. It's just going to replay your unit test and help the failure for that. Okay, if we go back to the example at the beginning of the presentation, if you remember, we have this contract. We have 2 functions, a buy function, which is going to check if you have enough money and mint some token, and a valid buy function that is stateless and just going to try to see if you provide enough token and enough Ether to buy it. Here you have two functions, buy, which is stateful, valid buy, which is stateless. Here again, start with the simplest one, valid buy, start with the stateless. What invariant can we have here? One simple one, really simple, is that if you send 0 Ether, you should not be able to have any token out of it. So you can define this as an assertion. So you call the function, you say, I'm sending more than 1, you call valid buy, this should never be reached. Like this should always fail because you are trying to buy something with 0. If you run this with Echidna, it's going to tell you actually you can do it with 1. And the reason for that is if you look a bit more closely to the formula, here you have a division and then a multiplication. If the number of tokens is below 10, the division is going to return 0 because it's going to run down. So the amount of Ether that you have to send is going to be 0. So for any token from 1 to 9, you can basically buy that for free. Does that make sense? Any question? I have hinted a bit the assertion mode. So in Echidna, we have what we call API. So we have 3 ways to define invariant. We have the Boolean properties that we saw with the first exercise. We have the assertion that we quickly saw. With like the previous slide, and we also support the DApp Foundry API. The DApp Foundry is mostly the same as the Boolean property, but you have this setup function and so on. Boolean properties, we already saw them. Assertion, you just add additional assert to the code base. And DApp Foundry that you are aware of. So for the next exercise, we are going to go on exercise 4. We are not going to do the exercise 3 today. And here we are going to use the assertion mode. So we're going to try a property where instead of using Echidna something function, we are going to use assertion. And let's take 10 minutes-ish for this one. Any question? Yeah. This one?
Would you mind going to, the example test? Thank you.
This one? Okay. The slides are also in the GitHub if you need them. Do you have any question regarding this one? Okay, okay.
I have a question.
Yeah.
So you mentioned system-level assertions, and let's assume in the case with the balances, you write a test and just make a transfer and make sure the balance is either increase or decrease. Mm-hmm. Is there a way to do this subsequently, like many more times, do these transfers away outside of just running a for loop and just doing a bunch of, does that make sense? I want basically to do a lot of transfers, but the state is maintained after each of them.
So it's what was already happening here. You are going to define an invariant where, the after the execution, the state should be which, this invariant should be true. Echidna is going to try multiple calls. If you remember on the previous example on exercise 2, Echidna was calling 2 functions. It was calling owner and then resume, I think. So here, Echidna could also call, if you have a transfer function, Echidna might call transfer 1 time, 2 times, 3 times, 10 times. It's just going to randomly try different combinations.
Okay, perfect. So let's say in a case like a lending protocol and so on, it would just try a random number of iterations of random number of things, and it would just see if at some point reaches an inconsistency.
That's correct.
Okay.
There is a notion, if you look at the configuration of sequence length, Basically, it's a number of calls before the state is reset to the beginning. Like, for example, if you say the sequence length is 1,000, it's just going to try 1,000 calls, and at some point, it will just reset the system to like the initial state.
Okay, thank you. And is there a way to kind of target its inputs to something? For example, like it's in Forge, I think. You basically can limit the inputs in some ranges.
So the best way to do that is to do input filtering in Solidity. We have some tutorial in Secure Contract about that, and we have some helper in a repo which is called Properties. Basically, you use modulo. So, like if you want to kind of narrow the input from an integer to like 100 to 1000, you can use modulo operation. You take like the uint, use modulo operation so that as a result, it's just going to be between this range. And so that the further doesn't waste time. You can also use require. You can just say, like require this input to be that number, but require will waste like resource from the further because transaction will revert.
Okay. Yeah. Thank you.
Okay, so here the goal was to use assertion, and we were trying to, break the transfer function. So here we inherit from the token. We call super.transfer to call like the function we want to test, and we define an invariant using assertion. So here the assertion is that it has increased. And yeah, if you run that with Echidna, it's going to break the invariance because of the bug. I'm going to go a bit quickly because we are running out of time. One thing you can also notice when you use assertion is that you can keep the assertion in your code if you want additional on-chain safeguard. This will allow you to have like invariant and post condition within your contract. It's going to cost more gas, and it can be complex enough bugs. So keep in your contract only assertion that you have a strong confidence in it, and for things that are not too complex. Quickly, there is a notion of multiple contract and composability. All the examples were mostly on one contract, but maybe like your system is using 5 or 6 different contracts. For that, you can use a specific flag, which is all contract. If you do that, instead of focusing on fuzzing one contract, Echidna is actually going to call all the function of all the different contracts. If you are looking for composability bug, that's really useful. There are a couple of additional exercises I'm not going to go through, but feel free to go through them after this day. There are many additional tools and techniques that you can do to check invariants. There are other further like Brony, DApp, Foundry. They might be easier to use, but in practice they might not be as powerful. We have been using Echidna for more than 5 years in our different audits, and we spend a lot of time making it efficient. There are other techniques based on formal methods, such as formal verification. The techniques are useful, they are powerful, but they have a lot of drawbacks. They are complex to use. They are time-consuming. There is this quote from the runtime verification CEO, basically saying that you need almost 9 times the resource to do formal verification on your code base versus what you need for development. So it's really intensive in comparison to fuzzing that you can, as you saw, use pretty quickly. Echidna has a lot of advantage that I did not cover. We have some functionality where, for example, you can try to look for transactions that are going to consume more gas if you are looking for, complex loop or things like that. You can do differential fuzzing where you try to apply on 2 different implementation of the same logic. You can do on-chain fuzzing, so you can provide an address and an RPC node, and Echidna is going to try to fuzz based on a state which is existing on-chain, and so on and so on. It's free and open source, obviously. Just for information, we are actually rewriting Echidna in Go. It's called Medusa. It's not as mature as Echidna. It's still kind of on an MVP phase, but if you are curious and you like to experiment with new tool, feel free to go through it. Okay, I hope that you enjoyed this session. To learn more about invariants and property-based technique, you can go to Secure Contract. We have the properties repo where we have defined existing invariants for different protocols that you can already reuse and just import in your contract. TLDR, you should start thinking about invariant, start in English, and then try in Solidity. Out of curiosity, who here is going to try Echidna on his next project? Perfect. And if you have any questions, feel free to let me know.